Chill, guys, chill. Jacobian is just a scalar triple product. So in this video, we want to show that the Jacobian, the basically while changing the coefficients, changing the parameters in integral. Let's say if we have dx, dy, dz as the dv, and if you want to change the du, dv, dw world, let's say, then you introduce like determinant over here, right? Which is basically dx by du, dy by du, dz by du, dx by dv, dx dy by dv, dz by dv, again dx by dw, dy by dw, dz. This is actually partial, not d, partial w. Okay, introduce the determinant, right, while changing the like coordinate system, and this is called Jacobian. And in this video I will show you that this is just actually a scalar triple product for 3D, in the 3D, right? So yeah, so that will be the main goal of this video. Now we will take cylinder to begin with. All right. Okay. Now note that let me take a cylinder. Yeah. So let's say if you want to represent this cylinder by equations, right? You can also represent this as, let's say, x square plus y square is equals to, if it is let's say a value r, if this is r, x square plus y square is equals to r square, and the z is from, let's say if this is h, z is going from 0 to h. If you write it like this also represents the cylinder, right? Basically the outer surface of cylinder, and if you want the entire inner surface as well, you can just write this as less than or equal to, right? So this is like representation in terms of Cartesian like coordinates, right? But this one is a bit complicated, and also over here this less than or equals to this equation, like let's say if you want to integrate, this also becomes messy. Like it becomes something like 0 to r, and then 0 to square root of 1 minus x square, 0 to h, dz, dy, dx. Here's the like height, or any thing that you want to. So this becomes messy. So in this cases, like when figures is, let's say, spherical conical cylinder, most of the time we use like the parametric vector representation to represent such figures, and in that scenario we get this. So yeah, so that I was just trying to introduce you to the like why we need the parameters. So I can write this as this figure is a set of vectors given by r, theta, and these two are not same, right? This is basically represents the output vector. Let me represent this by capital R then. Okay, r vector with r, theta, and as. So if they give us r cos theta, r sin theta, and as, this is basically x coordinate, y coordinate, z coordinate, right? And while r goes from 0 to this is r itself. Now again this is again same, so let us call this a, the radius a. R goes from 0 to a, theta goes from 0 to 2 pi, as goes from, let's say again 0 to, let's say this is capital S. So in this case, see, the conditions are also simpler, and the parameterization is also similar, and this gives us cylinder. If you want to integrate it, it's easy this time. Like radius goes, let's say first, height goes from 0 to h, theta goes from 0 to 2 pi, radius goes from 0 to a of dv, right? So it's easy to integrate, so we prefer like the parametric equations in this case. Now the only problem is, in this case our dv was just dx dy dz, right? Because that's how the volume is defined: length, breadth, height, the product of these three things, right? And yeah, this exactly matches the how x, y, z are set up in the Cartesian coordinate system. But over here, do you really think that again dv is just dr d theta dh? No, because if you want to just intuition, see, like if you do the dimensional analysis, this is in meters, this has no units, this is in meters, right? So the overall units is meter square, but volume has unit of meter cube. So clearly it doesn't work, right? Now, like if you want to slide intuition, like what should it actually have been? Okay, I'll show you over here in this cylinder. So let's say you are over here in this point of the cylinder, right? Yeah. Now in this point, let's say you are at some angle. This is basically if we're at the x coordinate line, you are at certain angle from here, right? Okay. Now a small change in angle means that you move from here to here, right? Yeah, this is a small change in angle, basically small change in theta. Now a small change in radius corresponds to this change, right? So basically this change is the change in the r vector due to the small change in theta, and this is the change in the r vector due to small change in radius, right? Now, due to these changes, the net change in the r, just due to these changes, the net change is the net change in the area. Let's say the net change in the area is this area, right? So basically, dA due to the changes is like, and if the changes is really small, we can assume that this is basically arc, but we can assume that as a line, right? And this one will just be r times d theta if this is the r and this is our dr, right? And this will just be r plus dr times d theta. But if dr is really small, we can say it as r d theta. Now this dA becomes r d theta times dr, right? R d theta times dr. So you see that dA in this case will just be r d theta times dr. Now if also there is a small change in the z coordinate as well, then yeah. So yeah, if this was in z, so this is our dv, right? And now since the base is just a rectangle, now we can easily find the dv, because we just need to multiply this area by dh, right? Or let's say dz. So this is our dv. So to find the dv, what you do is basically you try to see what is the change in this r vector, like how does this r vector that's giving us the coordinates, that's giving us the coordinates of the points, how does it change when there is a small change in theta, when the small change in radius, when the small change in z, and what volume does that change correspond to? And using that way you can find dB. So in this case dB, we found this out geometrically, right? This is r d theta dr dz. So it's 0 to s, 0 to 2 pi, 0 to a, and it's a dB just r d theta dr dz. Now this also matches dimensionally because this is meter, 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 so it becomes meter cube, right? If we try to integrate 0 to s dz, 0 to 2 pi d theta, 0 to a r dr, right? And sorry, over here the order of integration isn't matching. This is slightly wrong because the way I should write it is, first of all there's this limits of radius, so dr, limits of angle, so d theta, limits of height, so dz. Okay, now it matches. This is basically dz, it's same, just height and dz are same. Now this becomes just height times 2 pi times, this will be r square by 2, so a square by 2. So this becomes 2 cancels, pi a square adds, which is exactly the volume of cylinder, right? So yeah, now if you are able to find out dv, in that case this parameters, the condition and parameters make the integration really easy, right? So the only problem is how to find this dv. So in that case we found it visually, we found it geometrically, but it's not always possible. It's not always like too easy to find it geometrically. Let's say if you were like parameterizing in terms of spherical coordinates, right? In terms of this is we call it cylindrical coordinates. If we parameterize in terms of, let's say, spherical coordinates, in that case the x, y, z coordinates are really difficult. And like I mean it's difficult to visualize the changes in the r vector due to the small change in phi, theta, and the radius. Yeah, and geometrical it's not possible. Basically, I'll also show you the coordinates though. It's just rho. Okay, wait. It's rho sine. We don't need this though. Rho sine phi cos theta. Rho sine phi sine theta. Just if you are curious, rho cos phi. Okay, these are the spherical coordinates. This is x, y, z. Okay, but let's not talk about that. Now the only question is how do we find this dv in terms of if the parameterization is too hard, right? So yeah, so I'll show you. Now how we can find this is, let's draw another cylinder, or let's just erase this what we have drawn over here. Okay. Now, first of all, know that this r vector is the one that gives us all the points in this cylinder, right? So basically, if I input, let's say, some specific angle, let's say if I input this angle, this radius, and this height, our r vector will give me this point over here, right? Yes, r vector will give me this point. Now, again, if I just change theta by a little, my r vector might give me this point because this will just rotate by slightly. If I change r by a little, my r vector might give me like this point over here, this one, right? Because the radius change. If I point the s vector, it will just give me a point slightly above that point, maybe just this one over here, right? So this is how the r vector gives all the points. Now what I want to see, to find the change in volume due to the small change in r, due to the small change in theta, due to the small change in h. So we will first of all try to see how this r vector actually changes with respect to each of these components, right? So first of all, if I just see how r vector changes with respect to theta, right? So maybe this is the change, right? Change in r vector due to theta. Because yeah, we can see that visually as well, but even if we don't know, I'm just drawing a random direction. So and if you want to find it like algebraically, you need to do like partial r by partial theta, right? This just gives the change in the radius vector due to theta, and this is just basically, we know that our r vector is just a like combination of x, y, z coordinates, right? And all of these x, y, z coordinates are written in terms of it's just r cos theta, r sin theta times z. Now if you partially differentiate this will just be minus r sin theta, r cos theta times, now this will just be 0 because there's no theta in it. So this is how you find the change in the r vector due to theta. So you got this, right? Yeah. So we first try to find how the r vector changes with respect to theta, right? And then we try to find how the r vector changes with respect to the radius itself, right? Let me write it capital R vector again. That because that can make confusion, because capital R vector is basically giving us the position, different things. This is not a radius. This is just actually just a position vector. R vector is just the position vectors of all the points in the cylinder. Okay, now this is over here. Note that, and I'm just drawing the change in r vector, not the r vector after the change. This is the r vector when there's a small change in angle, but I'm just trying to draw not the final r vector due to after change, just the change. So if let's say if the theta changes between this angle to this angle, not sorry, that's not the word. Okay, I mean if the theta changes after that, this will become this vector, right? And so this is the change in r vector when the change in theta. So I'm just trying to draw the change, not the actual final vector. So if you use partial derivative, this can be represented by the change in r vector due to theta, right? And I already saw you how to partially differentiate this. Now let's say the change in r vector due to radius will be this line, right? This is the change in r vector due to radius. Now you can clearly see now not clearly. Now again the last one is change in r vector due to height, which might be something like in the third dimension. Like let's say if this is the plane. Okay, wait, let me zoom it. It might be in third dimension. Like how do I draw it? Over here, let's say it's coming out of this screen, or I don't know. Like it will actually be going. Wait, for that what I will do is I will try to show change due to r like this. This is change in r vector due to r, and our z is like this, which is pointing upwards. This is kind of xy plane, and this is pointing upwards because yeah, that's what happening over here, right? Now we want okay. Now we have like we can find all these three vectors, right? Just like how I find the change in r due to theta. So this is the change in r vector due to theta. Just like this vector, we can find all these three vectors, right? Using the same way. Right, let me, if you want me to find, let's say, change in r vector due to r, I can find it. Change in r vector due to r, this will just be r vector is just x vector combination of x, y, z vector. In this case, x is r cos theta, y is r sin theta, z is just, I don't need to give vector over here because this is just the components. I'm sorry for that. Okay, now z is just again z. If we differentiate this, this will just be cos theta sin theta 0. Similarly, if you want me to do it with respect to like z, this is just r cos theta r sin theta times g, and this is just 0 0 1. So you see that all three vectors, right? And I'm almost accurately drawing this. Okay, fine. Now we want the change in the volume due to these three changes, right? Now to find that, how do we find now the only problem is how to find the volume that included by these three vectors, right? What's the volume of this by these three vectors? Now what I mean is, like, due to these two change vectors, the volume encompassed is this volume, right? Now due to this final one, the volume encompassed is this volume, right? We just try to extend the vectors in all directions and try to form volume. So now we want this volume, right? And note that since the change is really small, all these vectors will be straight lines. Since the change is really small, all these vectors are actually straight lines. Now to find this, so first of all, we can find this. Let's say this is a vector, b vector, c vector. We can find this area using the cross product, right? Because we know that the cross product, the magnitude of this cross product is just a b sine theta, right? Now we also know that its area is just, if this is s, we know that the area of the base is just a times s, right? And if this angle between the a vector and b vector is theta, s is just b sine theta, so this is just a b sine theta, yeah, right? So you see like why cross product, the magnitude of cross product should give us the area. You see that, right? Because it's a b sine theta, and a b sine theta is also a into s, and a into s is exactly the formula of area for a parallelogram, right? And now the direction of the a cross b vector is perpendicular. Wait, I will also make a few changes over here. Let me try to give a general case where c might not be perpendicular to the surface. I will try to give a general case over here. Let's say if c is like this, we call this figure a parallelepiped, where the third coordinate system is not perpendicular. If it's perpendicular, we call it cuboid, right? A cuboid or a cube. Now let's say it's this case. It's just, I think it's too off. Well, let me not make it too off. I'm sorry for this delay. I want to make the figure to be really good. I mean understandable. It's just that the figure is slightly bent. You know what I mean? The figure is slightly bent. I mean, it's not going straight. Even if the base is like this, it's just tilted. This is the figure I want to show you. It again looks like cuboid though. I guess you get the idea. If you don't get the idea, like, you can just Google what kind of the parallelepiped. That's the kind of figure I'm trying to make, where this third axis is, it's just not perpendicular to the base. Okay, now we already know that to find the area of the base I can just use this, right? And the direction of cross product is actually perpendicular to the surface. So this is the direction of cross product that should be perpendicular to surface, right? So now this is the direction of cross product, and its magnitude will just be equal to the area of parallelogram. Now if I want to find the volume of this parallelepiped, I should just multiply the area of base with this height as, right, with this height. This is just a like thing for prism. For prism, to find the volume of prism, and in this case it's also a prism, find its volume by just multiplying the area of base with its height, right? Now let's say if this third vector makes an angle of alpha with the height, then, and let's say if its length is just c, then h will be c cos alpha, right? So this will just be a vector cross b vector dot c cos alpha. Now notice that here the angle between a vector cross b vector and c is also cos alpha, right? Because this is just a height is just a vector cross b vector, right? So since this is kind of u v cos alpha, where alpha is angle between u and b, this is actually dot product of u and b. Yeah. So I can write this as dot product of a vector cross b vector dotted with c vector, right? And yeah, so you see that, and this is actually known as the scalar triple product. This is known as the scalar triple product. And now you see that this scalar triple product is just written like this without any symbols, because a vector cross b vector dot c vector is just equal to a vector dot b vector cross c vector. So we don't need to give any symbols in between. So yeah, so you saw that this scalar triple product actually gives the volume encompassed by three different vectors, right? Volume of the parallelepiped found by three different vectors, right? So over here as well, the volume encompassed by these three vectors, over here, this volume will also, okay, this is height is a bit more than there should have been, I'm sorry for that. Okay, this volume will also just be the scalar triple product. Basically I can write it as a change in r due to theta cross change in r due to r dotted with change in r due to, this is not y, this is z actually. Why am I missing it? Change in r due to z. So yeah, you see that, right? And that's why now if you want to find dv, now let's try to find. Now let me tell you one more thing regarding how we find the scalar triple product. If let's say a vector is a1, a2, a3, b vector is b1, b2, b3. Now I guess you guys know that a vector cross b vector will just be the determinant of I, j, k, a1, a2, a3, b1, b2, b3, right? Now this determinant, if you expand it, this will just be I, a2, b3 minus b2, a3 minus j, a1, b3 minus b1, a3 plus k, a1, b2 minus b1, a2, right? So this is our like a vector cross b vector. Now if we try to dot this, with c vector, now you are just trying to dot this thing with c1, c2, c3, right? Now what will happen is the c1, c2, c3 will just like take the place of I, j, k, right? So that will just be c1 times a2, b3 minus b2, a3 minus c2 times a1, b3 minus b1, a3 plus c3 times a1, b2 minus b1, a2. And now if you want to write this in terms of determinant, you just need to substitute I, j, k by c1, c2, c3, right? That's obvious. So this one scalar triple product is actually equals to c1, c2, c3, a1, a2, a3, b1, b2, b3, right? Now if you want to write it in different form, notice that if we change two rows, the determinant will have negative sign. So this will just be equal to negative of a1, a2, a3, c1, c2, c3, b1, b2, b3. If you again change the rows, another negative sign will come in. So that becomes again positive. So this will be a1, a2, a3, b1, b2, b3, c1, c2, c3. So that's how we can evaluate the scalar triple product, right? Now, now, okay, over here. Now over here, we were over here. We wanted to find out the change in the b vector due to we knew that it's just the scalar triple product of change in r due to theta, change in r due to r, and change in r due to z, right? So yeah, I'm not writing this cross product. You can write this if you want to, but yeah, you know that it's a triple product, right? Now, how would you find change in r due to theta, right? Now, to find change in r due to theta, what you can just do is, this is the rate of change of the r vector, this vector that gives us the position, with respect to theta. This is the rate times the actual change in theta. You see that, right? Again, just like that, this change in r due to r is just the rate of change of r due to r times the actual change in r. Again, similarly, the rate of change in r due to z is the rate of change of r with respect to z. This is actually the partial rate of change because just depending on r times the z, right? You see that, right? Okay, so now I can write dv, I can write this as, so we have already proved that it's actually a scalar triple product. Now I'm going to show you how this actually also gives us the Jacobian, right? We want to show that it's actually Jacobian. So I'm just trying to verify that. Now we saw that this is actually just partial r by partial theta times d theta cross partial r by partial r times d r, and dotted with partial r by partial z times dz, right? Now, first of all, since these are just constants, I can take them out, right? I can take them out of this product because the constant can be taken out, and then multiply and again take it out of the brackets. So this is just actually partial r by partial theta cross partial r by partial r dotted with partial r by partial z times d theta dr dz, right? Okay, now after this, dv will be equal to, now we know that like partial r by partial theta, if let's say r has three components x, y, z, in that case this vector will just be partial x by partial theta, partial y by partial theta again, partial z by partial theta cross. So now again this vector, we need to give a vector over here actually, right? I'm just missing a lot of things. Now again, partial r is just partial x by partial r, partial y by partial r, partial z by partial r, dotted with partial x by partial z, partial y by partial z, partial z by, sorry, I'm so sorry. Now also don't forget a d theta dr dz. Okay, then dv is equals to, now again, if I take cross product, and we know that this is the determinant, right? We just verified it already earlier. So this will be a determinant of partial x by partial theta, partial y by partial theta, partial z by partial theta, and then partial x by partial r, partial y by partial r, partial z by partial r, partial x by partial z, partial y by partial z, partial z by partial z. So d theta dr dz. Now in this case, just to visualize, we want a cylinder, right? Now, even if it was not a cylinder, right? Even if let's say it was just some other figures where let's say we were changing from x, y, z to u, v, w coordinate system, right? And if x was some function of u, v, w, y was also some function of u, some other function, g function of u, v, w, z was some function of u, v, w. Even in that case, the same would hold true, right? dv would just be dx by du, dy by du, dz by du, and then dx by dv, dy by dv, dz by dv, dx by dw, dy by dw dz by dw times du dv dw, right? So this holds true, and you see that this is the Jacobian in 3 dimension. This is what we call Jacobian in 3 dimension, and this is usually written as the dv is, if it's dx dy dz, this is written as partial of x y z with respect to partial of u v w times du dv w. This is how Jacobian is usually written, as a fraction, right? And yeah, we showed you that this is just 3D volume, right? Just a triple cross product. Now in this 3D case, it's 3D volume, right? And in 2D case, again, if it was 2D, that would just be 2D volume, which is also given by determinant. To get that, you can just take the, if you just take the like magnitude of the cross product with 2D vectors, that also gives us a determinant, which I have shown in my previous video. So even in 2D, that this is all true. Like dx dy would just be dx by du, dy by du, dx by dv, dy by dv times du dv. This is just hold true. This will just hold true in any dimension, because determinant always gives us the n-dimensional volume of the n-dimensional parallelepiped, right? So that's how it works actually. And yeah, so and in Jacobian, if you look at it in the way of a row, this basically gives us the change due to u, right? If you look at column, this basically gives us the change in the x vector. So yeah, these are some things that help me to visualize other shops as well, right? So yeah, and also the one thing is, like, you can change to any coordinate system, right? And also you can also begin with any coordinate system. It's not necessary that you start with x, y, z. This should also work. Like du dv dw would also be partial of u v w by partial of x y z times dx dy dz. Or like, or let's say, if you want, even if you like want to transfer from pqr coordinate system to u v w, that will still work. Like you can, it's so general, like dp dq dr will just be partial of pqr by partial of u v w times du dv dw. If you want to remember this, just see it as this being cancelled and you get pqr. So that's a good way to see it, right? Okay, so this was it. I think this should have been helpful for you, because yeah, much of the time we are just doing Jacobian without even understanding how it's working, right? So I think that this definitely gives you a feel. This definitely gives you an understanding. And to make this video, this is my third attempt. And I think this attempt was somehow fair. Yeah, it was not that bad as the previous attempts. And yeah, I do hope you enjoyed the video. Thanks for watching. If you loved it, do share with your friends. And look forward to seeing you in the upcoming videos too.